Okay, so we're going to look at how to graph a logarithmic function. In this example, I'm going to try to graph y equals log base 3 of x. The first thing that I'm going to do is actually graph y equals 3 to the x, the exponential of that. Log base 3 of x is actually the inverse of this base 3 exponential. So in the last unit, we looked at how to graph these functions. I'm going to go ahead and graph that function, then I'm just going to reflect all of those key points over the line y equals x by switching their x and y coordinates to show you what the graph of this new function should look like. Then we'll go ahead and talk about domain and range and all that fun stuff, asymptote lines. Okay, so I said I'm first going to start off by graphing the exponential function y equals 3 to the x. The initial value of y equals 3 to the x, or y-intercept, would just be 1. So I'm going to go ahead and plot that point of 0, 1. And then in the previous unit, we said with the base being 3, every time I move 1 unit to the right, that y-coordinate is just going to triple. So the next point would be 1, 3. The next point after that, again, when I move 1 more unit to the right to 2, its y-coordinate would need to triple. That would become 9. And then when I moved over 1 more unit, 3, I would triple that again. That would become 27. That should be enough points in that direction. And then if I had moved to the left, instead of 0, 1, I would have been cutting the y-coordinate it would have been being multiplied by a third each time. So then when I moved to negative 1, I would have a y-coordinate of 1/3. And then when I moved another unit left to negative 2, I would have a third of that for the y-coordinate, which would make 1/9. I'll go ahead and do one more. When I move to negative 3, just to keep it same number of points on each side, a third of that would be 1/27, like that. So there I can see several points that would be on the graph of y equals 3 to the x. I'm going to go ahead and change the color of them so that they are all the same color, just for consistency here. Make them all red. So there's that, and I'll go ahead and show that the function does pass through those points by going ahead and actually graphing y equals 3 to the x here, so that you can see that function is in fact passing through every one of those points that I've plotted, so you can see that I've graphed that correctly. Now, to graph y equals log base 3 of x, that should be a reflection over the line y equals x. So I'm going to go ahead and draw in the line y equals x here. Maybe we'll make it green and dashed there just so we can see that line in there. So I just need to take all of these coordinates and reflect them over that line, which means I need to switch all of their x and y coordinates. So this one right here, for instance, negative 3, 1/27th, should become 1/27th, negative 3. And then negative 2, 1/9 should become 1/9, negative 2. And then negative 1, 1/3 would become 1/3, negative 1. The other point there I have of 0, 1 would become 1, 0. Next point that I had there of 1, 3 should become 3, 1. The next point that I had there of 2, 9 should become 9, 2. I'm just switching the x and y coordinate of all those points. And then finally, the last one I had there of 3, 27 should become 27, 3. And you can see that I have plotted all of those points. Again, I'm going to go ahead and change the color on all of those just to keep it consistent. I'll go ahead and make all of those blue. So I've just graphed the exponential like we talked about in the previous section, and then I've reflected all the points by switching their x and y coordinates to reflect it over the line y equals x. That's how I'm graphing log base 3 of x for that. Okay, so now finally I want to just go ahead and actually use this graphing utility to graph that function passing through those points so that you can see that I've done it correctly. Unfortunately, this will not let me type log base 3 of x into this. It won't let me type a base for the logarithm. The good news is I know how to get around that since I know the change of base rules. So I'm going to do y equals, here on Desmos to show this, I have to go to functions. I'm going to do log of x divided by, back to functions again, log of 3. Again, I'm just graphing. This is how you would have to type it into a graphing calculator as well if you didn't have one of the newer ones that had the log base feature, since it wouldn't let you type in a base 3 logarithm. So I'm using the change of base rule to do this, so I can use the common log. This is just me trying to show the graph of log base 3 of x. And you can see that it does, in fact, pass through all of those points that I had previously plotted. So hopefully looking at those two graphs, you can see that the y equals log base 3 of x is just the reflection of y equals 3 to the x over this line y equals x. It's because they are inverse functions of one another. Now we need to go ahead and talk a little bit about certain characteristics. Like before, when we graphed the exponential functions, we looked at the y-intercept, we looked at the domain, we looked at the range, and we looked at the equation of the horizontal asymptote line down here. So now we're going to go ahead and discuss those same things for this logarithmic function. Okay, so now I want to go ahead and talk a little bit about the domain, the range, in this case the x-intercept instead of the y-intercept like with the exponential functions, and the asymptote line for this. So the domain here, in interval notation, the x values that are represented here is everything from here, from 0 over, but it doesn't include 0. So we have parenthesis 0 to infinity for our domain. That's just a way of saying all real numbers greater than 0 for that. Our range would be our y values, and we can see this graph continues going down forever, and it keeps going up and to the right, although it goes to the right significantly faster than it's going up. It does continue going up forever for this. So the range here is actually from negative infinity to positive infinity. The graph covers everything in the y direction for that. So all real numbers or negative infinity to positive infinity in the interval notation for the range. We said the x-intercepts now. This doesn't have y-intercepts because the y-intercept is where the x value is 0, and this doesn't contain 0 in the domain for that. So just looking at the y-intercept here, whereas the exponential function had a y-intercept of 0, this one will have, of 1, or this one will have an x-intercept of 1. So the x-intercept there is 1. And then finally, the asymptote line, that line that this graph is approaching, where the exponential functions had a horizontal asymptote line that they were approaching. Now that we've reflected everything over the line y equals x, this now has a vertical asymptote line that we are approaching right here, where x is 0. So the vertical asymptote would be x equals 0. The horizontal asymptote for the exponential functions that we were dealing with before was y equals 0. Now we've switched y and x for the inverse here, so now we have x equals 0. We have that vertical asymptote line that the graph is approaching right there. So there's some key characteristics. Now, again, as we talk transformations, as we start to add other numbers into this, maybe where we add something inside the logarithm versus adding something outside of the logarithm, putting numbers out in front that could stretch, compress, reflect, all that kind of stuff, then we need to look at these characteristics again. Just think about what you know about transformations already and how that's going to change this information.